Okay, so we have at this point completed our initial survey of what enthalpy is, the whole delta H thing. We have completed a problem set from chapter 6. We have learned about everything that we can at this moment about enthalpy. And so now we're switching gears just a little bit. We're not cutting ties with enthalpy, but instead we're going to weave it into something that is called entropy. Oh man. See the word right here? Entropy. So there's enthalpy, that's heat, and then there's whatever this thing is, entropy. These two chapters are generally in a chemistry book kept far, far apart from each other, and I will never understand why. What I could do is to take what we've learned already about enthalpy, give you a test, and then in a couple months bring back chapter 16, which we're actually beginning right now, and then ask you to remember a lot of things about enthalpy. And while that's sometimes effective, what I've taken to in the last few years is putting them together, because I think it makes more sense for flow. So I hope that you will agree, because again, you will see some delta H stuff today, so we're not cutting ties just yet. Okay, so what are we doing? Or I'm sorry, what have we done? We have done what's called the first law of thermodynamics. We've been working with, as I say here, delta H stuff. We've been learning about enthalpy. The law of conservation of energy is the first law of thermodynamics. It says that heat, which is a form of energy, it can change forms, but you can't create it and you can't destroy it. So it sounds a lot like law of conservation of mass, right? Which is why we balance chemical equations. So we've really been talking about that, changing forms of energy. We've been doing what's called affectionately energy bookkeeping. Where is the energy? Where is the heat? How is it transferred? Is it endothermic or exothermic? Are bonds breaking? Are bonds forming? That's all stuff we've been doing, and we've just kind of been keeping tabs on it. It's like keeping a checkbook. Where's the energy going? Am I adding or subtracting it? And you continue on. The issue here is we have never accounted for why a process would happen. And when I say process, I mean chemical reaction. We haven't accounted for why it would happen in a given direction, as in towards the products or maybe in the reverse direction towards the reactants. And we haven't even really accounted for if it would even occur in the first place. Because we've talked before about how reactions aren't all created equal. And so one may be a lickety-split, super fast reaction, and one may be a little snail of a thing that barely gets anything going. That's where the new stuff comes in, okay? So what we're going to be doing today is talking about processes being thermodynamically favored or not, and then this whole entropy thing, because it certainly factors in. So first off, let me tell you about this phrase here, spontaneous process. It's a reaction that will continue to occur without doing anything else to it. And I'll give you some examples of what that means. But it's basically saying once it starts, it ain't stopping. It's going to continue to go until it's done, I guess is the easiest way to say it. However, the way that AP likes to term this is thermodynamically favored. The reason I present both phrases to you is because in the textbook excerpt that I've offered you, it will talk about spontaneous processes, but AP likes the verbiage here, thermodynamically favored, or by the way, thermodynamically unfavored. So please understand that what's in red is what you have to know it by. And here's the reason for their change. The reason why AP went with thermodynamically favored. When you hear the word spontaneous, do you or do you not think that spontaneous means fast? I mean, be honest with yourself. When you hear that word, you think, ooh, fast. No. And that's the problem. Because a spontaneous process doesn't have to be fast. It can actually be quite slow. And that is where you have to understand that thermodynamics and rate, kinetics, for instance, it has nothing to do with anything. And we haven't talked about kinetics a lot. But basically, and in fact, really at all, that's coming up in another couple of units. But what you want to understand about rate is that it's how fast. So some reactions are super fast and some are kind of slow, But it doesn't matter whether it's fast or slow. It can still be considered spontaneous because it just has to continue to go without me having to do anything to it. So that's the reason for the change. The word spontaneous, the AP people felt was a little bit ambiguous, so they went with thermodynamically favored. Okay, examples to try to help you understand what this really is. Ice melting, for instance. I might do some initial work to take an ice cube out of the freezer and set it on the counter, and then I just walk away. Will the ice stop melting because I'm not looking at it? No, it continues to melt, and that's a spontaneous process. Does it happen immediately? No, takes some time, a little slow, but it happens. A ball rolling down a hill. I may do some initial work to give it just the teeniest push at the top of the hill, but once that ball starts rolling, it will not stop until it gets to the bottom. Because think of how weird that would be if the ball just all of a sudden stopped in the middle of the hill. Yeah, that's just not going to happen. So it's a spontaneous process. I put in a little energy right at the beginning, and then it just goes. And steel rusting is another great example. All I need is a little scratch in my clear coat and through my paint, and the rusting process will happen because all it takes is iron and oxygen, both of which are readily available in any of our garages or parking lots. So steel rusts very slowly, but it is a spontaneous process, okay? So I want you to understand it's not about fast or slow. It's about will it go if I get it started. So what we're going to be doing now is predictions of if a reaction would be favored thermodynamically or if it would be spontaneous. And we're going to use this goofy thing called entropy to do it, okay? So fair enough so far? All right. So what the heck is entropy? I'll give you this crazy word and I don't even define it until 3 slides in. So here we go. Entropy. It is a thermodynamic quantity, so it will have a number associated with it. And it's a measure of the randomness or the disorder of the system. If you do any looking online or on Pinterest or whatever for funny little chemistry things, there's a typical one that I've seen 100 times, and it shows a scientist in his office, and his office is a mess. I mean, it's just awful. And it says, as a caption on the picture, entropy happens. Ha ha ha, come on, it's funny. A disorder happens. And it's the truth. In fact, as we will see, that's kind of how the universe works. So, okay, are you laughing? You probably didn't even laugh. Okay, whatever. So entropy, it's abbreviated by a capital S. And if you're a thinker here, you may recall in a textbook somewhere, we saw some S's along with some H's. Remember that appendix? Okay. That'll be coming later. The units are measured in joules per Kelvin. Or sometimes you'll see it joules per Kelvin mole, which is kind of like, the mole of reaction and things like that. So no big change. Entropy is dependent on the state that the reaction occurs in. So it's dependent very heavily on temperature and pressure. That should make sense. If you increase the temperature of something, do the molecules not begin to rattle around like crazy little 5-year-old children on sugar? Yes. Yes, they do. So higher temperature, more disorder. And pressure is another thing. Pressure actually works kind of in the opposite direction. If you reduce the pressure on something, you actually allow it to expand further and take up more space. And that's actually an increase in disorder. So kind of FYI. The entropy of the universe is increasing. The universe is expanding day by day. And so to follow suit, it got to go along with what the universe is doing, for goodness sake. Any process that increases the entropy. Ooh, did you like that? I want to see that again. You ready? Ready? Watch the red. Here it goes. Bloop. Oh, I love it. Awesome. Okay. Any process that increases the entropy of the system is thermodynamically favored. So any chemical reaction that's going to create more disorder within the system is going to be something that's very likely to be a favored reaction, and it will occur, okay? So if you want to start thinking big picture, if you're a chemical engineer here, you need to know about entropy because you want to be doing reactions for your company that are thermodynamically favored because you don't have to work as hard, right? If it's not thermodynamically favored, you got to do a heck of a lot of work to actually get this thing to make some money for your company. So little, reality snippet right there. Okay, so If you also think about it too, for instance, if these last 2 bullet points, if you're like, now, Mrs. Seagrave, are you sure with all that stuff? Well, yeah, I mean, think about it. Disorder is actually the most probable thing. If you clean your room and you live in your room for a month, is it going to stay perfectly neat and tidy? Of course not. I'm a realistic person. And similarly, I give you an example of a deck of cards. If we have a nice 52 card deck in our hands, perfectly put together, and it's, ace, king, all the way down to my 2, and it's perfectly in order in each one of the suits, hearts and spades and whatever. If I throw that deck into the air, what's the chances that that deck is going to land on the ground all together exactly the way that it started? Yeah, of course it won't. Disorder is most probable. Okay, so it's thermodynamically favored. So to understand entropy just a little bit, I have a picture for you. Consider a gas. It's on one side and the valve is closed. So these 2 tealish colored bulbs on each side, imagine that it's 2 flasks kind of turned towards each other and stuck together. And then this line in the middle right here, that would be a valve. So right now all the gas is on one side. Well, the question's going to be, what happens when I open the valve? Hey, that's an easy question. You kidding me? This is AP chemistry. If I open the valve, ooh, that was the best one yet, huh? Want to see it again? Okay, here you go. Open the valve and it spreads out. And it spreads out until it reaches some semblance of an equilibrium. So notice we have 3 particles on one side and 3 particles on the other side. So the gas spreads, and that is an increase in entropy. It's an increase in disorder because what you're doing is you're allowing those particles more room to groove, and that's more disordered because they're further spread apart. Okay, does that make sense? So simple example. Another way to simply explain the idea of entropy is with states of matter. If you think about solids, particles are tightly packed, right? Well, that's very little disorder. In fact, those particles just barely vibrate at all, which is why you don't feel the chair or the bed or whatever it is vibrating underneath you right now. It should be a little creepy if everything vibrated. But very little entropy, very little disorder. When you go to a liquid, the particles are still tightly packed, but they do have a much better ability to slip and slide past each other, which is why water pours so easily and why you can't pour, a desk. Sounds strange. And so liquids have a little more entropy, a little more disorder. And gases, of course, are free to move all around. They're the least tightly packed. And so they have considerable entropy, lots of disorder within the particles. So from highest to lowest entropy, you can think about solids, liquids, and gases in that manner also. Okay, so pretty simple. Okay, another thing I'd like you to think about. So I have solid carbon dioxide and I have gaseous carbon dioxide. And by the way, solid carbon dioxide, anybody know what that is? It's called dry ice. And obviously the gas version is just regular carbon dioxide, what we exhale. So which one has more entropy, more disorder, the solid or the gas? Okay, hopefully you got the right answer. We just talked about that on the previous slide. The gas version is because it has more particle motion, hence more disorder. And then I did actually give this answer away here with the nitrogen. Nitrogen at 1 atmosphere, nitrogen at 0.01 atmosphere. Which would be more disordered? Okay, the answer is the 0.01, and that's because when you have less pressure, those molecules spread out further, they take up more space, where if you take a look at the 1 atmosphere, those particles are going to be jammed a little tighter together, which starts to look like a solid just a little bit, So if you think about it that way, hopefully that makes sense, and it's just offering you another way, again, to think about entropy. Some of your homework will be like this, so pretty simple today. Okay, so what we're talking about, it's the second law of thermodynamics, okay? So remember, the first law of thermodynamics was basically energy bookkeeping, the law of conservation of energy. And now with the second law of thermodynamics, we're talking about these thermodynamically favored processes only being possible, okay, gotta take that back, not only, but being possible if there's an increase in entropy of a system. So essentially, the second law of thermodynamics is about entropy. If you increase the disorder, it's probably a thermodynamically favored process. Notice I did say probably. Another thing I want you to keep in mind, entropy and energy are not the same because energy is really enthalpy. And these are two different things. So remember that energy or enthalpy, we always conserve that, again, based on the first law of thermodynamics. Whereas entropy, we're actually always increasing disorder within the system. And so not the same, okay? They're very similar, entropy, enthalpy, but understand that they do not have any connection to each other in terms of similarity. They are related, but they are not synonyms. No way, Jose. Alrighty. Effects of temperature on thermodynamically or thermodynamic favorability. Ooh, big words. So this is just kind of a side note sort of thing. Entropy changes are primarily determined by heat flow. Exothermic reactions give off heat to the surroundings, right? We talked about that. Exothermic, give off heat. What that's going to do is it's going to lower the overall energy of the system, because the system is what is releasing the energy. And we talked a lot about how chemistry favors stability in terms of the system, and lower energies within systems is a good process. It ends up being a thermodynamically favored process. Also, if it's an exothermic reaction, you give that energy to the surroundings, and then what happens to the molecules in the surroundings? If you put heat into the surroundings, the molecules start moving faster. That increases entropy. That increases disorder. So what you can see here in these big bolded blue phrases here, these are like check. We have got a really good process because we lower the energy of the system, which is what chemistry works based on, and we've increased the entropy of the surroundings, which is how thermodynamics works. So exothermic reactions tend to make a process thermodynamically favored. Now notice what it says. But being exothermic does not automatically make the process thermodynamically favored. Part of the reason for that deals with how much energy is maybe already in the system. Sometimes it deals with temperature, okay? So more on that later, just kind of hold the thought. But for now, understand that if it's an exothermic reaction, it generally will be thermodynamically favored, and that's because of a connection to entropy, as well as just sort of plain old regular chemistry. Okay, so sort of a rundown. This is a slide that's really kind of meant to be a mid-presentation review. So exothermic processes release heat into the surroundings. They increase molecular motion of the surroundings. Hence, they increase entropy. Okay, you can also look at that as saying negative delta H will release heat to the surroundings, increase molecular motion, increase entropy. And the delta S, so this is the first time we're seeing that symbolism here, but remember S is entropy. The delta S will be positive. The process is favored. Again, thermodynamically favored. So you want to start understanding more of these positives and negatives. So we had to memorize the H ones, right? H, negative, exothermic. H, positive, endothermic. Here now we have S, positive. It goes with the exothermic part, and it is a favored process. Whereas your endothermic is going to be opposite. So a positive delta H, it absorbs heat from the surroundings. That actually decreases the molecular motion of the surroundings, and it will decrease entropy. And as you guessed it, the delta S value will come out to be negative, and it's a process that is not thermodynamically favored. Okay, so negative delta H means exothermic. Negative delta H goes with positive delta S. Okay, we do a little opposites attract kind of thing. Positive delta H, which is endothermic, positive delta H goes with negative delta S. Okay, opposites attract. Okay, another little side note here. The impact of the heat transfer on the surroundings will be greater at lower temperatures. Okay, if you think about two different scenarios, if you have a system that's hot already and it has 2,000 joules of energy, and you want to put 50 more in, it's not really going to have a big effect, right? Like 50 to 2,000, it's like a drop of a hat. But if you try to release that same 50 joules of energy into a system that's relatively cold and only say has 10, you're going to make a bigger impact. So some of that, and this is again, some of that thing where I said, well, more on that later. When you talk about how much heat might already be available, that's going to also impact the thermodynamic favorability and everything in between. Okay, so just sort of a side note on that right now. All right, so moving on. Yeah, this is a lot of info. There's sort of a lot of things we've thrown out here. So what really matters? Bet you're wondering that. Well, we are going to do some math here. So what really matters? First off, it matters that you know what delta S means. It means a change in entropy. It matters that you know what entropy means, that it's disorder of a system. And it matters that you know how to calculate it. So we're going to take the quantity of heat in joules, which you're going to see is actually enthalpy. And we're going to also need a temperature because, as I just said on the previous slide, the heat available in the system kind of matters also. So we're going to have a Kelvin value of temperature, and we'll do a little division, and then we'll be able to actually calculate some entropy values for ourselves in a relatively simple manner. So yeah, do recall the quantity of heat here. This is Q, this is delta H. So if you get a negative value, it's exothermic, a positive value is endothermic, and we want to make sure that this all fits together really well. So now notice the slight change. Notice that there's a negative sign right here. Okay, that makes total sense. Makes total sense. If a reaction is exothermic and the delta H is negative, then the double negatives, cancel, and they make S positive. So do you see? I have to have that negative sign in there. So what you see in the blue box, that is the equation that we're going to use to do a couple of little calculations with entropy values today. Okay? All right, so last slide is right here, and this is just some examples. So I'm asking you here to determine the delta S value, or the entropy, at 25 degrees Celsius, and you're just going to utilize the equation that was on the previous slide. So it's, remember, delta S equals negative delta H over T. So negative delta H, well, that means that would be positive then, right? Because it cancels. And I'm supposed to have my temperature in Kelvin. So could you do me a quick favor? Pause the video. Convert 25 degrees Celsius to Kelvin, please. Okay, so my hope is you came up with 298 and you were able to then put something together that looks a little bit like this. Because my final answer ended up as a weird decimal, I just did a multiplication to get out of kilojoules and into joules, because notice that this was a kilojoule and it's completely fine to do it that way. So 419 kilojoules. Now what does that value tell you? You have a positive delta S, which means it's a spontaneous process, or again, really that should say thermodynamically favored process if I stick with AP. Okay, in the next example, you may be able to figure this one out already. You had a negative up here, and now this is a positive. So when you factor in this, that negative now sticks. And to take my negative 778 divided by the 298, I'm going to get a negative value, and that, my friends, is not spontaneous. Or, to stick with AP, it is not thermodynamically favored, meaning that if I try to run this reaction of this particular process here with the antimony and the oxygen and the carbon, if I try to work with that, this reaction just doesn't really want to happen, especially not at room temperature, 25 degrees Celsius. Whereas this reaction with the antimony and the sulfur, if I want to react that with the iron, that's a process that likes to happen. And so whether it's fast or slow, it likes to happen thermodynamically favored. All right, that's it for today. Record your questions, and we will talk tomorrow.